Why do they do every test before the homecoming week?
I don't have any. I don't have any tests this week, so.
I have 2 tests tomorrow though. 5.
Well, that you can't count that one though. You know, that's not my fault. Put it that way.
True.
All right. So today we start trigonometry. So up into this point, we had kind of been reviewing some ideas from algebra and then some ideas from geometry. And today we're going to start trigonometry, right? So the big picture here, actually, before we do this. So in geometry, we started with SOHCAHTOA, and that was defined for right triangle or acute angles in a right triangle, right? Couldn't do sine, cosine, and tangent on a non-acute angle. You certainly couldn't do it without a right triangle. Everybody's okay with that idea?
Yes, sir.
Our order of business in this chapter bless you.
Oh, not one of the sneeze attacks again.
Is that we want to now define sine, cosine, etc. on any angle. So no longer do we want to be tied into a right triangle or tied to specifically acute angles. So that's what we're going to be building out towards the goal in this chapter. So that's our goal in chapter 2, is going to be redefining how we're thinking about sine, cosine, and tangent. So we're no longer married to this right triangle, but we can now do sine, cosine, and tangent on any angle. Yes, Sydney? Of course. Everybody's okay with this so far?
Yeah.
Okay. All right. So we're going to start here in 2.1, just kind of talking about angles. So we want to talk about the different ways we have to measure angles. Okay. One way we have to measure an angle is with degrees. That's what you guys would have used almost exclusively in geometry. And another way is radians, and there's a third way called gradians, but you don't need to worry about that as a high school student. And this is what we're going to be talking about here to start today, is this other way of measuring an angle called radians. So let's start with our definition of what a radian is then, right? So we say that a central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. Woof, Mr. Kulik, what the heck does that mean? Right? There's a bunch of vocab in there from geometry that probably we don't remember super duper well. That's okay. Let's kind of go through and walk through what this definition is saying and what these vocabulary really mean again. Everybody's cool with that plan? Okay. I'm going to do this with a picture. So let's say that we have a circle. When we say a central angle, we're talking about an angle whose vertex is at the center of a circle. So this guy, CAB, is a central angle. When we say intercepts, we mean that the arcs of the angle intersect the circle at some point. And then when we talk about an arc, we're talking about that distance of that curve from C to A. I'm sorry, C to B. When we write an arc, we name it with 2 letters, and we put like a little curvy top hat on it to show that it's an arc. And you remember what a radius is, right? What's a radius? Yeah, it's the distance between the center of your circle and any point on the circle. Is AC the only radius in this picture? No, right? AB would also be a radius. So what are we saying here? We are saying that if AC, if the length of the radius is the same as the length of that arc, then angle CA, well, the measure of angle CAB is 1 radian. So that's what our definition is saying. Now, we have these 2 units that we can measure an angle with. We have degrees, we have radians. Whenever we have 2 different kind of units available to us, what do we need to make next? If you have inches and you have centimeters, what else do you need? If you have inches and you have centimeters, what else do you need? If I tell you something is 214 centimeters, well, does that mean anything to you? Not much. What would you rather have that measurement in? Inches or what? Yeah, something that you're familiar with, right? So what do we need to go between the 2? We need a conversion factor to go in between radians and degrees, just like we need one to go between like inches and centimeters, right? we're much more comfortable talking about angles in degrees than we are in radians. It's certainly helpful, at least in the beginning, to have a way to convert back and forth so that we can associate like what kind of radian is similar to what kind of or degree measure so that we can build out some intuition, right? Everybody's okay with that? Sure. Sure, Mr. Kulik, sure. Okay. So let's look at a situation here. Okay? Oops, that's not where that was supposed to land. So let's say we have a situation like this. Okay. So if I look at this picture, what's the measure of the angle CAB gotta be? Yes, of course. 180, great. And what's the measure of the arc CB? So like how far is it like that? Ava? Well, I'm the distance though. So yeah, we measured arcs with degrees in geometry. I'm asking for the distance, so the measure of it, the arc length. Well, it's going to be half the circumference of the circle, right? And how do you do the circumference of a circle? What's the formula for that? Well, it's 2 pi r. So our arc measure should be pi r. Everybody's okay with that? So if I know that one radian let's just say we know that a length 1 radius is cut by a 1 radian angle. So I know that like a length of 1 on my radius is going to convert to a 1 radian angle measure. So since 180 degrees paired up with pi r, and I know that 1 radius is 1 radian, basically that just kind of drops itself out, and we can say 180 degrees is equivalent to pi radians. That's our conversion factor. So if I have some measurement in degrees, the conversion factor I'd multiply it by to get the radians should be pi radians over 180 degrees. And if I have some number in radians, what's the conversion factor I need to multiply it by to get it into degrees? I have pi radians under 180 degrees. Or if you want to think about it as like a visual, to go from degrees to radians, you multiply by pi over 180. To go from radians to degrees, we multiply by 180 over pi. For those of you that are in a chemistry class or have been in one recently, that probably looks like a familiar way of writing your conversions, right? Just kind of like, what are the two things going back and forth and the factor I used to go in between? Okay, let's do some examples. Dimensional analysis is what you called it in chemistry. Okay. Let's do a couple examples. Let's convert 90 degrees to radians. So what do I need to multiply 90 degrees by to get it into radians? Anybody want to help me out? Thank you. Pi radians over 180 degrees. Now, the convention in trigonometry is whenever possible, we'd like to write our radians in terms of pi. So to do that, I need to kind of reduce this multiplication problem as I go. So do we see a common factor between 90 and 180? What's the common factor between both of them? 90, right? So if I divide 90 by 90, that becomes 1. If I divide 180 by 90, that becomes 2. So we could write this as pi over 2 radians. That's the preference. Or you could write this as a decimal. So if I go to our calculator and I do pi divided by 2, I could also write this as about 1.57. So why do you think we prefer the pi over 2 version to the 1.57 version? I said that was going to be the convention, was going to be leaving it in terms of pi. Yes, more accurate. Why? There is no rounding. Yes, excellent. Yes, of course. Now, there's certainly instances where the rounding could be unavoidable, and that's fine. But if possible, we'd like to not deal with that. So here we want to convert 152 degrees into radians. What do I need to multiply by in order to do that? Pi radians over 180 degrees. Again, if possible, we'd like to keep that. Do you see a common factor between 152 and 180? Definitely 2, right? Because they're both even. So if I do that, that becomes 76 and 90. What do you notice, though? They're still even, right? So you can certainly divide another 2. So that should be 38 and then 45. And then I don't think there's another factor there, right? Or if you type that into your calculator, you'd say it's about 265. Do you know how to reduce fractions on your calculator? I did that reducing by hand. You can do it on your calculator, though. You want to see? So I'm going to do 152 divided by 180. And then I'm going to press Math and then select the frac command. So that what that's telling us, the calculator, is to do 150 divided by 180 and then give my answer as a fraction. 38 over 45. That's nice, isn't it? As we're doing stuff, I'll continue to show you like things your calculator can do that can be helpful to you. Next up, so C is asking us to go from 2 pi over 5 radians into degrees. Maybe I'll just write it this way. What do I need to multiply this by to end up in degrees? Excellent. 180 over pi radians. So when I multiply this, the pi's are going to cancel. 5 goes into 180. How many? Into 180?
Oh, wait, no.
Way more than 5, right?
Goes into
16.
16, yeah.
So it would be 36. And then 2 times 36 is 72. Or, if you wanted to, you can just type it all into your calculator. So again, the pi's I just canceled by hand, so really I'm just doing 2/5 times 180. 72. So far, so good? Okay. The last one was 1.6 radians. What do I have to multiply this by? Anybody?
I got it.
Shoot, homie. Give it to me. Oh, you're fibbing. Pi something. Excellent. 180 degrees over pi radians. So here, like the radians cancels out, but there's no pi in the 1.6. So I have to hang on to that. And because there's no pi to cancel, there's no way to get this into an exact number. So this is one that just has to go into my calculator. So 1.6 times 180 divided by pi. And 9167. So I'm going to change that. Let everyone know I rounded. Yes, certainly. Okay. Okay. I want to talk next about arc length of a circle. Do you remember what this is from geometry? We use the letter S to represent the arc length of a circle. We did theta, that's the measure of the central angle, divided by 360 degrees times 2 pi r, which is the circumference of the circle. Notice here that we can reduce this a little bit though, right? So the 2 and the 180 can reduce. So you could write this as theta times pi r over 180. Maybe we should make sure that we're being clear and say theta is the measure in degrees. But if I notice here, what if I take an angle in degrees and multiply it by pi over 180? What do I get? Here, let me I'm going to do this. That'll make this a little bit clearer. I'm going to add a D subscript to the theta to indicate that it's in degrees. So I take an angle in degrees, I multiply it by pi over 180. I just change that angle to radians, right? Ooh, that looks a little bit cleaner there, right? Where our arc length is just the angle in radians times the radius. Ooh, that's nice. So let's make that a definition. And we should probably write down that formula if we're in degrees. Now let's do some examples. So notice that here we're in radians. So I can just do the angle measure in radians times the radius. I don't need that. Just write hard equals. So I just go to my calculator. Calculator and type that stuff in. Isn't that lovely? How easy is that? Bloop. Keep in mind that these questions all have a unit attached to them, so your answer should have a unit attached to that. Here, an arc length should be in the same linear unit as your radius. If I look at, yes, of course. If I look at the next example, my angle is in, or measured in degrees. So I should use my other formula. And that's a little complicated looking. I'm going to use that fraction command on my calculator. And I get about 2,653. So far, so good. If I look at the last one, I notice that my angle is back in radians. So I'll go back to my radians formula. But here we're looking to solve for r. So we're told s, we're told theta, looking to solve for r. Well, I just need to divide by that 213, and that'll give me my r. So R is about 8,451. And then we were in centimeters. What do you guys think? No big deal, right? NBD. Right? Pretty easy so far, yes? Just like converting some units and using a formula. Okay, well, let's make it a little bit more challenging. Here it says, find the perimeter of a sector with a central angle of 1.7 radians cut from a circle with radius 5. Who remembers what a sector is? A piece of what? So it's a piece of a circle. What kind of piece of a circle? It's like a slice of pizza. Like a round pizza, though, not a Jets pizza. Sure. So here's my sector. There's my sector. Everybody's good? I've labeled the sector. The R's is like the radius because this is like, you know, like some slice out of a circle, right? Like some slice out of a pizza. So the radius of the circle is still going to be the sides of that sector. And then the arc length, I've labeled S. That arc length is going to be the curved side of our pizza slice. Everybody's cool? So if I want the perimeter of that thing, I have to take R plus S. Everybody's cool? The perimeter is just the distance around something. And S, I know, since we're measured in radians, so here I have 5 plus 5 plus 8.5. And the unit in this problem was centimeters. So that's it. I'm all done. Does that feel okay? Yes, Ava. Correct. So the uppercase R I'm using as a subscript on the theta because the formula for arc length is different depending if your angle's in degrees or radians. So I'm just putting a subscript on the theta to remind everybody that I'm using the radians version versus the degrees version. That's the angle. Or in this case, the central angle measure. I'll do that for you. Feel good? Okay. We'll do one more example, and then we're on to the next section. I know it's really exciting. So exciting. All right. So here we say that a car has 18-inch diameter tires on it. Yeah. It's traveling 15 miles per hour. how many revolutions per second are the tires making on the car? Oh my. All right. So I'm going to start with kind of what I know. So I know 15 miles per hour means we go 15 miles in 1 hour.
Yep.
And what I'm going to do is I want to convert this into revolutions per second. Okay, well, the seconds part should be easy. I know 1 hour is 60 minutes. And then 1 minute is 60 seconds. So when I multiply through, the unit will now be in miles per second, right?
Yeah.
Everybody's cool with how I did that part? I think it's dimensional analysis. Nomenclature is like calling something sodium bromide. Now, here's the trickier piece. How am I going to go from miles to revolutions? So, one circumference is going to equal 1 revolution, right?
Yeah. So, however,
Mhm. So my circumference would just be 2 pi r
so 2 pi 9.
times 18. Oh yeah, times 9. Yep. Inches though, what unit is this in? Miles. So let's convert the miles to inches first, then we'll tack that other conversion at the end. Exactly. So I remember that 1 mile is 5,280 feet. And I remember 1 foot is 12 inches. And then I remember there are 2 pi times 9 inches in 1 revolution. So miles, canceled the miles, feet with feet, inches with inches, and we're left with revolutions per second. Now all we have to do is the arithmetic. So again, that's a lot of fractions there. I'm just going to use the fraction command on my calculator to make this easy. So I'm going to do the top together. I have 15. The ones don't matter, right? If we're multiplying by 1, it doesn't mean boo diddly. So I have that times 5,280 times 12. And on the bottom I have 60 times 60 times 2 pi times 9. So I get about 4.669 revolutions per second. But it's this right here. This was the key observation, is that 1 circumference is the same as 1 revolution. That was the key conversion factor that wasn't something that like you might consider common knowledge, right? Going from miles or from hours to seconds, not too bad. From miles to inches, not too bad. But that last piece we had to kind of think about. All right. So last time we talked, we were talking about reviewing SOHCAHTOA, right? That's trig functions of acute angles. So if I have some right triangle with angle theta, and I label the sides then opposite, adjacent, and hypotenuse respectively, SOHCAHTOA tells me that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Everybody's cool?
Was that trig sum?
FNS is just short for functions.
Gotcha.
Now, did you ever wonder why, like, there's 6 ways to write a ratio, right? Because you have 3 choices where you can't repeat anything, so you have 2 or 3 times 2 possibilities of writing one of these ratios. Why isn't like hypotenuse over opposite, or hypotenuse over adjacent, or adjacent over opposite? Why aren't these corresponding to a trig function also? You ever wonder that? Well, they do correspond to ones. You just didn't bother, nobody bothered to tell them to you in geometry. They all have names.
That's terrible.
No,
It's not,
nobody tells them to you in geometry. So, we're going to define 3 new trig functions at this time. The first one, CSC, is called cosecant. And that is the reciprocal of sine. It is hypotenuse over opposite. We're going to have secant, which is the reciprocal of cosine, hypotenuse over adjacent. And then we'll have cotangent, which is the reciprocal of tangent, adjacent over opposite. So when I memorize this, this is the way that I do it. So these 3 new trig functions, we're going to have to memorize also, but I don't memorize the ratios for these. I just remember that sine goes with cosecant, and cosecant just the opposite, the reciprocal of sine. Secant goes with cosine, so I don't have to remember the cosecant or the secant definition. I just remember that it's the reciprocal of cosine. Tangent goes with cotangent, so I don't remember the cotangent definition. I just remember that it's the reciprocal of tangent. Does everybody kind of get what I'm saying there? I think it just makes the memorizing easier if you just remember which pair together and then they're just reciprocals of the one you already knew. Okay. Let's do an example here. Just kind of using these things. So this one says find the exact values for all 6 trig ratios in the right triangle. So far, so good. How do I do sine? SOHCAHTOA is
Opposite over.
Great. So what's the opposite
Uh,
for the theta in our picture?
5.
5. And what's the hypotenuse? You don't know. Can we find it?
Yes.
Yes. How do we do that? Math, specifically Pythagorean theorem. Great. So how would I write my equation then? Excellent. Remember, the hypotenuse is always the c that's by itself in a squared plus b squared equals c squared. So 5 squared is 25. 2 squared is 4. 25 plus 4 is 29. So x is the square root of 29. Everybody feel good? Is that the way we're going to leave our final answer, though? No. Why don't? What don't we like about that? Because radical in the denominator. Excellent, Ellie. Do you remember how to get rid of it?
Times the denominator. So, what are 29?
Yeah, we multiply by the square root of 29 to the top and bottom.
5 times square root of 29 over 29.
Great.
Yeah.
Now, we should be able to do cosecant really easy, right? Because cosecant's just the reciprocal of sine. Everybody agree? So what else should I write here
What?
for cosecant?
Oh.
Yeah, very good. So notice that Nora took this one to make the reciprocal, because if you took the other one, what would you have to do again? You'd have to rationalize the denominator again and then have to reduce, and it's just like a mess. If I take the one before we rationalized, there's nothing to do. Yippee! Okay. Cosine is? You mean adjacent over hypotenuse.
Oh, yeah.
The adjacent side is? 2. And the hypotenuse is? Square root 29. Again, we got to rationalize that denominator. We'll do it the exact same way. And then what will secant theta be?
29 over 2.
Square root 29 over 2. Okay, and then tangent is?
Opposite over
Great, and what's the opposite?
5.
And then the adjacent is 2. Nothing to do there though, right?
No, sir.
That one's fine the way it is.
5.
Cotangent is 2 over 5. What do you guys think? Piece of cake, right? All right. What if we do this? Let theta be an acute angle of the right triangle. If sine theta is 1/3, what are the values of the other 5 trigonometric ratios for theta? Well, one of them's easy, right? Cosecant is
The opposite.
the reciprocal, so 3 over 1. I'm just going to write 3. And we need cosine and secant, and then tangent and cotangent. I would start first by drawing myself a picture. So here's my right triangle. I'm going to pick that label or that angle and label it as theta. Sine is opposite over hypotenuse. So 1 and then 3. To find that adjacent side, though, we'll call that x. I have to use the Pythagorean theorem. Yeah. So a squared plus b squared equals c squared. Remember, c has to be the hypotenuse. So subtract 1 from both sides is 8, and I square root both sides is the square root of 8. If I break that into square root 4 times square root 2, that's 2 root 2. So cosine should be 2 root 2 over 3. Everybody happy? What's secant going to be then? The reciprocal. Yep, but what do you notice? Yeah, rationalize the denominator. What should I multiply to the top and bottom? I wouldn't do that. Just the square root of 2 should be enough. If you do 2 root 2, it's fine, but you'll have more reducing to do at the end. When I multiply those two together, that's just a regular 2, right? So I have a 4 on the bottom. So far, so good, everybody? Okay, tangent is opposite over adjacent. Got to do that same thing again. So I get 2 root 2 over 4. And then cotangent is just the reciprocal, so that would be 2 root 2 over 1, or just 2 root 2. So far, so good? And then no big deal, right? Any different than what you did in the delta math, really? You have 3 more ratios to use, but like, it's the same thing, right? The techniques are the same. Let's do another example. Well, this is a good one. Find sine of 30 without using your calculator. Well, guess what I'm going to start by doing? Drawing a picture. So there's my right triangle. There's sine 30, or I'm sorry, 30 degrees. What's the other angle have to be? 60. Does that ring any bells from geometry? Recall the 30, 60, 90 triangle has side lengths with ratios x, x root 3, and then 2x. Yep. The way I remember this is root 3 is like 1.69. So like smallest opposite the smallest, 30 opposite 1, yep. 60 opposite the middle, 1.69, 90 opposite the big, 2. So if I have this then, sine of 30 is opposite over hypotenuse, which just reduces down to 1/2. Oh! What's the other special triangle that you would learn about in geometry other than 30, 60, 90? The 45, 45, 90. That has ratios x, x, and x root 2. Do I expect you to remember that? I do. But that would be a good candidate for what? Your half sheet, right? That'd be a good thing to go on your half sheet. Okay. What if I say next to find sine of 16 and then secant of 78? Notice, what did the directions not disallow here? Your calculator. Oh, good. So I'll just use my calculator to do this then. I'm going to check real quick before I do this my mode. What mode should we be in? Degree, because I noticed that in both cases the angles are measured in degrees. So I'm just going to do sine of 17. That's easy enough. Feel good there? How do I do secant, though? I don't see a secant button on my calculator. Remember, what's the relationship between secant and cosine? They are reciprocals. So instead of typing secant of 78 in my calculator, I'm going to do 1 over cosine 78. And I'm done. Boom. Boom goes the dynamite, right? Okay. What do you guys think? So far, so good? This was pretty easy so far? Okay. Tomorrow we start, or next time we start building out our definition of, or trying to extend these definitions, sine, cosine, tangent, secant, cosecant, cotangent, to include angles bigger than 90 degrees. Ooh. And that'll be the next 2 sections. We'll spend doing that until we settle on our final definition of sine, cosine, tangent, cosecant, secant, cotangent. At this point, you guys should be able to do up through 42 from the homeworks. Yeah, but they're like not too bad, right? Like 12 of them are converting from degrees to radians and radians to degrees. Like just typing in your calculator and pressing enter, you know, multiplying by pi over 180 or 180 over pi. Not too bad. That's a quarter of the homework. That's like, okay, those are like 10-second problems, you know. So it's not so bad. This is where I'm going to stop, though. Like, that feels 2 sections is plenty, right? You guys got questions on stuffs? So with the delta math, remember that I screwed up the due date on the delta math. Like, wasn't due yesterday at 8 a.m. before I gave you a chance to work, or before, yeah. So that's due Sunday. It's part of Sunday's homework set.
Oh, so the delta.
Yeah. So if you didn't finish, get it done this week, but I'll be checking with the next problem set. So if you are done, kudos to yourself. Good job being efficient, getting stuff done. If you haven't finished yet, you have till Sunday, no rush. Apologies if you were like in a mad panic trying to get it done by Monday morning. No biggie. It's done, right? One less thing for you to worry about. Done is done. Still counts the same. Okie dokes. Okay. Anybody have questions about anything? No?